Hi, before we start today's lecture, I just want to explain to you that at the end of the class, I have to run out and catch a plane. So if you have to discuss any other administrative matters, you should do it now because you won't find me after class. I just couldn't take this weather. You know where I'm going? Seattle. That's the story of my life. Okay. So nothing else? Okay, so yes.
Is there going to be an equation sheet for the midterm and so is it possible to see?
You will get the equation sheet. You want it now? No. With the exam? Yeah. Yeah, I don't give it out before, but you will have all the reasonable equations in that sheet. Okay. Because it is, you know the reason for that, right? Reason is that some of you may be going into medicine, right? And you control the anesthesia on me one of these days in the future. If I held back the equation sheet, I know you will hold back the painkillers. So it's just making a deal. The way things are done nowadays, I made a deal with you guys. Okay. So I couldn't sleep last night because today is when we're going to solve Maxwell's equations and get the waves. Just couldn't wait to get to work. It's great. No matter how many times I talk about it, I just find it so amazing. So here are these great Maxwell equations. I'm going to write them down. Okay, those are the equations. The first one tells you that if you draw any surface and integrate B over that surface, namely you're counting the net number of lines coming out, you're going to get 0. That's because lines begin and end with charges, and there are no magnetic charges. So any line, if you look at any magnetic field problem, the lines don't have a beginning or an end. They end on themselves. So if you put any surface there, whatever goes in has to come out. That's the statement of no magnetic charges. This one says, yes, there are things that manufacture electric field lines called charges. They make them and they eat them. And depending on how many got in a volume, the net will decide the flux out of that volume. This one, without that, used to say electric field is conservative field, it defines a potential and so on. But then we found in the time-dependent problem, E dot dl is a rate of change of the magnetic field. So changing magnetic field sustains an electric field. And this one says a changing electric field can produce a magnetic field. In addition, a current can also produce a magnetic field. This is what we have to begin with. Now, I'm going to eventually focus on free space. Free space means we are nowhere near charges and currents. And the equations become more symmetric. This has got no surface integral. That has got no surface integral. Line integral of this guy is essentially the rate of change of flux of that. And line integral of that guy is minus the rate of change of flux of this. All right. Now, if I'm going to get a wave equation, the triumphant moment is when I do this and do that, and out comes the wave equation. But if at that moment you have not seen the wave equation, you're not going to get the thrill. So I have to know how many people remember the wave equation from the first part of the course. Okay, so I think I have to remind you of what that is, right? It's a bit like explaining a joke, but still I have to do that because otherwise we won't have that climactic moment. So let me tell you what one example of a wave equation. People have seen them before. Here's the simplest example. You take a string, you tie it between two fixed points, and it has a tension T. Tension is the force with which the two ends are being pulled. Then you distort it in some form, and you release it, and you see what happens. Now let's measure x as the distance from the left end, and y as the height at that x at that time t. The wave equation tells you an equation governing the behavior of y. Tells you how y varies. Now, if you want to do that, you may think you have to invent new stuff, but you don't. Everything comes from Newton's laws. That's, to me, the amazing part, that you have these equations, then, of course, the Lorentz force equation, then you got Newton's laws, and that's all we have up to this point in the course. So there should be no need to invoke anything beyond Newton's laws to find out the fate of this string. And namely, we're going to apply F equal to ma, but not to the whole string at one time, because a is the acceleration, and whose acceleration are we talking about? Piece of string here, piece of string there, they can all be moving at different rates. So you pick a tiny portion, which I'm going to blow up for your benefit. That's a piece of string. Its interval, it lies under region of length dx. In other words, you take a dx here and look at that string. It is being pulled like that with the tension T, and it's being pulled like this with the tension T here. That's the meaning of tension, pulled at both ends. If this was a perfectly straight segment, there'll be no net force on it because these forces will cancel. But if it's slightly curved, then this line and that line are not quite in the same direction, and the forces don't have to cancel. So let's take that force and write its vertical part. If this angle is theta, t times sine theta is the force here, minus t times, because t is pointing the opposite way, minus t times, let me call this theta 1, and let me call theta 2 is the angle you have here. You understand? The vertical forces restoring the string to where it was is what I'm focused on. So you resolve that force into a vertical part up, and this one has a vertical part down. Now, if theta 1 is equal to theta 2, they cancel, and that's what I just said. But theta 1 and theta 2 generally are not equal, because if I go to the top of the string, for example, this end is pulling this way, that end is pulling that way, there's a net force down. So you have a net force because this angle or the tangent to the string is changing with position. That's why they don't cancel. Now, the approximation I'm going to make is that theta is small, measured in radians, and I remind you that sine theta is essentially theta minus very small corrections, and cosine theta is 1 minus theta squared over 2 plus corrections, and tan theta, which is the ratio of these guys, is theta plus other corrections. For very small theta, you forget that, you forget that. You keep things of order theta in every equation. So for small angles, cosine is just 1, and sine theta is theta. If you do that, and sine theta and tan theta being equal, I can write it as tan theta 1 minus tan theta 2. But that's in the approximation, where sine and tan are all roughly equal. That is really t times dy dx at the point x plus dx minus dy dx at the point x. Are you with me? Dy dx from calculus, you remember, is the slope. It's a partial derivative. Why is it a partial derivative now? Can you tell me? Yep. It can depend on time, and I'm doing f equals ma at one instant in time. So I don't want to take this guy's slope now and that guy's slope an hour later. I want them at the same time, that fixed time. Now, what do I do with this? Have I taught you guys how to handle a difference like this? There's one legacy I want to leave behind is what to do when confronted with a difference like this. You have any idea what to do? Pardon me? Multiply by 1. Multiply by 1. Then what do you do with that? I'm asking you to evaluate the difference between this guy at x plus dx minus the same thing at x. What is it equal to approximately for small dx? Okay, let me ask you another question. Suppose I have f of x plus dx, and I subtract from it f of x. What is it equal to? Pardon me? If I divide by delta x and take the limit, it becomes a derivative. If I don't divide by delta x, this is then df dx times delta x. There may be other corrections, but when delta x goes to 0, we may make that approximation. That is the meaning of the rate of change. If I tell you here's a function and that's the same function somewhere to the right, what's the difference? That's what the role of the derivative is, to tell you how much it changes. So this slope changes from here to there. Therefore, it's the derivative of something which is already a derivative. So it's d2y over dx squared times delta x. In other words, the f I'm using here is itself dy dx. The df dx is then the second derivative. So that's the force. Now that force we must equate to ma. That's the easy part. What is the mass of this section, this portion of string? If the mass per unit length is mu, that's the mass of that section. Then what's the acceleration? Acceleration is the rate at which y is going up and down. That is d2y over dt squared. Canceling the delta x, we get this wave equation, which says d2y over dx squared minus mu over t d2y over dt squared is 0. And that's the origin of the wave equation. Anytime you get something like this, you call it the wave equation. I'm going to write this as d2y dx squared minus 1 over v squared d2y dt squared equal to 0, where v is square root of t over mu. I use the symbol v because this will turn out to be the velocity of waves on that string. Namely, if you plug the string and make a little bump here, let it go, the bump will move, and v is going to be the speed at which it moves. The speed of waves is determined by the tension and the mass per unit length. Now, I want to show you that this really is the velocity of the wave. I mean, how do we know that's the velocity? It's got dimensions of velocity, but maybe it's not the velocity of this wave. Maybe it's something else. I want to show you that v stands for the velocity of the waves in this medium. The way you do that is you ask yourself, what is the nature of the solutions to this equation? I mean, what if y of xt satisfies the equation, what can you say about its functional form? What functions do you think will play a role? Does anybody have any idea what may be involved in this? What kind of functions may play the role? Pardon me? Sines, maybe. With single oscillators, when you had something is d by dt squared, you had cosine omega t. And whatever you can do for t, you can do for x. You can have a cosine in x. So you might think it will involve cosines and sines and exponentials. All that is true, but it turns out the range of solutions is much bigger than that. I'm going to write down for you the most general solution to the wave equation, namely, what's the constraint it imposes on the function? The answer is this. Y can be any function you want of x minus vt. I don't care what function it is. So if I call z as a single variable x minus vt, y can be a function of this single combination x minus vt. In other words, y can depend on x and y can depend on t. If it depends on x and t in an arbitrary way, of course, it won't satisfy this equation. But I'm telling you that it depends on x and t only through this combination. x minus vt, it'll satisfy the wave equation. In other words, here's a function. You don't even have to think. X minus vt square over some number, x naught square. That's a completely good solution to the wave equation. I guarantee if you took this, it'll satisfy the wave equation because it's a function only of x minus vt. A function that's not a good function is y equal to e to the minus x squared minus v squared t squared. That's not a function of x minus vt. That won't satisfy the wave equation. So why is that true? Why is this true? That's what I want to show you. Let us take dy dx. Remember, y depends on this, only on this combination z. Therefore, it's equal to df dz times dz dx. But z is x minus vt, dz dx is 1, so it is just df dz. Now, let me rush through this and do it one more time. Everything will go the same way. You will get this. But how about dy dt? If you want dy dt, again you take df dz times dz dt. But that gives you, so this should be written as a partial. dz dt is df dz times minus v. Can you see that? By the chain rule, you take any function you have, first differentiate with respect to z, then differentiate z with respect to x or with respect to t. If you do an x derivative, you get 1. If you do a t derivative, you get minus v. Now, if I do it twice, again, I don't want to spend too much time. If I do it twice, I'm going to skip the intermediate step. I'll get a minus v and a minus v squared. It follows then that if I took 1 over v squared times that, can you see that now? 1 over v squared d squared y dt squared is the same as d squared y dx squared. Therefore, to satisfy the wave equation, it can be any function at all as long as it depends on x and t in the combination x minus vt. That is just a mathematical fact. You just have to do the chain rule. You will find that is true. But more importantly, I want you to understand what it tells you about the wave propagation. Let me pick x naught equal to 1 for convenience. Let me plot this guy at time t equal to 0. This solution looks like e to the minus x squared, which is a function like that, at t equal to 0. What does it look like at t equal to 1 second? Think about it. T equal to 1 second, it looks like e to the minus x minus v whole square. That means it's the same bump shifted by an amount v. See, this function x minus v squared behaves with respect to x equal to v the same as the original function around x equal to 0. Whatever happens to this guy here happens to that guy at distance v to the right. You can see that if you wait t seconds, it would have moved a distance vt. That's why you understand that v is the velocity of propagation, because what this is telling you is that if you start the system out with some configuration at time t equal to 0, later on the function looks like the same function translated to the right at a velocity v. That means its profile. Whatever profile you have will just move to the right. Now, can you think of another family of solutions besides this one? Why should the wave move to the right? Yep. Do you understand that if it is x plus vt, you go through this derivation, you'll get a plus v squared instead of minus v squared, and that doesn't matter. So the answer is that the most general solution of the wave equation is any function you like of x minus vt plus any function you like of x plus vt. This will describe waves going to the right. That will describe waves going to the left. And you can superpose them because it's a linear equation. You can add solutions. This is what I want you to know about the wave equation. Okay, this is one example of how the wave equation comes and what the meaning of the symbol v is. Okay, now let me go to the old Maxwell equations. Now I want to do them and ask myself, I'm going to write down a solution, and I'm going to see if it obeys these 4 Maxwell equations. If I write down a solution for the electric field and the magnetic field, they have to obey all those conditions, those 4 equations. That means, let's take first the case of working in the vacuum, when there is no current, when there is no charge. So you want a surface integral of E on any surface to be 0, and the surface integral of B on any surface to be 0. Look at the surface integral first. You understand this is never going to be non-zero. This will be non-zero near matter, but we are far from any charges, so there is nothing to enclose in their volume. There are no charges there. Look at those 2 equations. I give you a function and I say, tell me if it satisfies Maxwell's equations. What do you have to do? Operationally, what is it that you have to do? Any ideas on what you must do at this point to test? Any ideas? What do you have to see of a potential solution? Come on, this is not the New York subway. You can make eye contact. So what is this? You have no idea what you may have to do? What if I give you a function and say, see if it satisfies the wave equation? What will you do then? Take the function and then what? Yes? Yes, take x derivative, y derivative, and all that, second derivative. If it vanishes, you'll say it satisfies it, right? That's what it means to satisfy it. Now, if I give you fields E and B that depends on space and time, and I want you to say, verify if it satisfies this, what do you have to do, is what I'm asking.
Come up with a situation.
No, it must be true in every situation. In other words, what's the surface on which this integral is done? On what surface do we do the integral? Pardon me? Closed. But beyond closed, anything else? Where is it located? How big is it? Pardon me? I didn't hear that. It could be anywhere, and it could have any size, it could have any shape. And it must be true for all those surfaces. So if I just give you a field, E of x, y, z, and t, it's a lot of work, right? Draw all possible surfaces. On them, you can take the surface, divide it into patches, do the surface integral patch by patch, and you better keep getting 0. Then you're done with that. Then you take the magnetic field. Then the other 2 Maxwells tell you, take a loop, any loop, and go around that, do the line integral of B. That should be the flux crossing it, the electric flux or magnetic flux. And it should be done for every loop and for every surface. You realize that looks impossible. But there is a quicker way to verify all these equations. And the quick way is the following. If these equations are true for a tiny loop, in this case, if true for a tiny volume or a tiny surface enclosing a tiny volume, then it's true for big ones. And likewise, if true for a tiny loop, it is true for any arbitrary loop. In other words, if I can show that at any arbitrary point, if I pick an infinitesimal loop or an infinitesimal surface, and these guys satisfy those equations on an infinitesimal thing, it's going to satisfy it on a macroscopic thing. That's what we want to understand. How does that come about? It comes about due to a very beautiful way in which we define the sum of 2 surfaces. So here is a surface. I'm going to take everything to be a cube, but it's not important. Here's a surface. Let's call it S1. And it's got its outward normal. That's the definition of surface integral. You draw the normals pointing outwards, and you take E dot dA on every face of the cube and add it. The area vector is defined to be outward pointing normal to every face. So you take the little cube. E has got a E may be pointing this way there or that way there, but you take the dot product of the area and you add them. Then I take a second cube here. Let's see. And it's got its own outward normal. This is surface 2. Now imagine gluing this guy to this guy so it looks like this. You glue this common face. Bring that surface over and glue them with that face common to both. Then I claim that the surface integral on this one plus the surface integral on that one is the surface integral on the union of the two. In other words, let's see, take one cube, take another cube, and that surface integral will be the same as on a longer object. I don't know what this is called, something over that. The two cubes used to be sharing this. Do you understand why? Let's understand why the integral on this guy, which is if you want two cubes joined to form a rectangular solid, that surface integral is the sum of these two surface integrals. Think for a minute about why that is true. If you compare them piece by piece, this face matches that face. This face matches this half. This one matches that half. But something is missing in this that's present here. Do you agree? What is it we don't have? What's missing in the uni? Yes?
Two sides equal to both.
The two common faces are missing in the big surface. But it does not matter. The two common faces do not matter because when you do the surface on the first one, the outward normal will point out of that, whereas if you do it on the second one, the outward normal will point into the other one. When you glue them together, the common face has opposite orientations. Consequently, the surface integral on the big solid is equal to surface integral, sum of the surface integrals in the two small solids. Do you follow that? That's the way it works. And then you can go on adding more and more pieces to this, right? And you can build, like Legos, you can build an arbitrarily complicated blob. And remember, these are all very, very tiny volumes. So you can build them up. It look like a big thing. It may look like a pyramid. If you look very closely, you'll have the steps like in a real pyramid, but the steps here can be made arbitrarily small. Therefore, if the surface integral was 0 on every little piece that made up the big object, then it's going to be 0 on the big object, because the integral on the big object is the integral of the tiny pieces that make up the big object. This is a very profound idea, because the big object has fewer surfaces than the small ones, because when you cut it, you create two new surfaces, but they don't contribute between the two of them because they cancel. And in particular, if the surface integral had not been 0, but because of matter it was equal to charge inside volume 1, and this right-hand side of this one was the charge inside volume 2, you can see that the surface integral on the bigger surface will be the sum of the two charges. So anything you're trying to prove about surface integrals, even if the right-hand side is not 0, if it is true in a tiny cube, true in a union of two cubes, and then on the union of any number of these tiny guys, therefore on any surface. So that's the thing to remember. So what we will do then is not to take arbitrary surfaces, but infinitesimal surfaces, and we'll prove for them that the Maxwell equations are satisfied for the solution I come up with. Then you're guaranteed that it'll work for an arbitrary surface. When you do line integrals, this is for surface integral. Line integral is even easier. Suppose I'm taking a line integral of some function around this loop. This is loop L1. I take a line integral of some field on L1. Then somebody wants to do a line integral on L2 that looks like this. E dot dl on L2. You agree that this plus that really is the same as the line integral on the union of the two loops, where you delete the common edge. You have to understand this. I will not leave any child behind. You have to know why this is true. I'm taking a lot of time so you know where it's coming from. If you compare an integral of any field on the big rectangle compared to the two squares, the only difference is that the two squares had these two sides. But they were doing them in opposite directions, so it does not matter. So if the line integral of this, for example, was some flux coming out of this one, the line integral of that was the rate of change of flux coming out of that one. If it was true, then it's guaranteed that the line integral on the big rectangle will be the sum of the fluxes, or the rate of change of the fluxes coming out of both. So any Maxwell equation, if it's true for a tiny square, infinitesimal square, will be also true for anything bigger. There's only one subtlety when you do loops, and that's the following. If you're living in a plane, you can prove the result for a plane in the plane of the blackboard, because there is no loop I cannot form by joining these guys. But we live in 3 dimensions, so that we may have a loop like this floating in 3 dimensions. Then what you have to do is you've got to find any surface with a loop as a boundary, maybe this dome. Then the integral on that, so let me hide this for you. This is the part behind. This is the part you can see. That's the same as tiling it into little squares and doing an integral on each one of them like this. Okay, you have a dome of some big building. You take little tiles and you tile the building. Then all the interior edges cancel, and all that remains is the edge, that is the edge of the original surface. So even in 3D, it's going to work. But now you should be ready for loops that are not lying in the xy plane. So you will have to prove it for the 3 independent loops. You will have to prove it for an infinitesimal loop in that plane, infinitesimal in that plane, infinitesimal in that plane. If it's true for 3 independent directions, then by combining those little pieces, you can make yourself any surface you want. In other words, I'm saying you can build, given a rim, you can build any surface with the rim as the boundary if you can take the little flat pieces in any orientation. And it's enough to have them in the x, y, yz, and zx planes. So the strategy that I'm going to follow, this is something one can skip, but I wanted you to know the details if you really want to know where everything comes from. I'm going to write down or search for a solution to Maxwell equations. I'm going to make it have a certain form. Remember how we do this with equations. We assume a certain form, stick it into the equation, play with some parameters till it works. I'm going to make it work on infinitesimal loops and infinitesimal cubes, and that's going to be enough. Because if it works on a tiny loop, works on a big loop, works on a tiny cube, works on a big cube or arbitrary surface. So let us write down the functional form that I'm going to use. The functional form that I'm going to use looks like this. I'm going to take an electric field that is entirely in the z direction, and the z field will depend on y and t, and I'm going to take a magnetic field which is going to be in the x direction, and the b field is going to depend on y and t. So let me tell you how my axes are defined here. This is x, this is y, this is z. The electric and magnetic fields, the electric field will always point along the z-axis. The magnetic field will always point along the x-axis. They will not vary as you vary x or z. They will vary only if you vary y by assumption. In general, it can vary with everything, but I'm trying as a modest goal to find a simple solution which has a dependence on only 2 of the 4 possible coordinates. Depends on only y and t rather than x, y, z, and t. I mean, let's get any solution. We cannot get every possible one. Let's get something, and something I assume has this form. So this is called a plane wave, because if you take the plane y equal to 0, E and B are constant on that plane, because when y is fixed at some value, E and B are not changing as you vary x or z. So you should think of it as plane after plane, and on each plane the field is doing something. It's doing the same thing. If I draw a plane here, that field is a constant. E is a constant on that plane, and B is a constant on that plane. On another plane, it could be a different constant, but it doesn't vary within the plane. It varies from plane to plane. So that is not an axiom. That's not a law. That's an assumed simplicity in the function I'm looking at. There's no theorem that says that every solution to Maxwell equation must obey this condition. In general, these functions will be functions of x, y, z, and t. The trick will be superposition. If I can get a solution that depends only on y and t, and you can get a solution that depends on z and t, I can add them up and they will still be a solution, because the wave equation is linear. You can add solutions. Then our sum of the two solutions then will be a function of y and z. And you can bring in the x and so on. So you do the simplest one, then you can add them. So here is my function, and I have to know what I can say about these two functions. You understand? In general, the electric field has three components. The magnetic field has three components. Each of them depends on four quantities, x, y, z, and t. Big mess. In our simplified solution, the only unknown component of E is Ez. I'm assuming there is no Ex and there is no Ey. And there is no By and there is no Bz. Now you might say, why don't you go a little further? Kill the B also. You can try that. If you kill the B, you will find the only solution you get is everything equal to 0. So by trial and error, we know this is the first time you can get something interesting going. So if you make it simpler than that, you get nothing. You can make it more complicated, but not simpler. Okay, so now, will this satisfy the surface integral condition? Let's check that. So what do I need to do for that? Here is, I have to take a cube, right? Let me take the cube. It's infinitesimal, but I'm just keeping it near the origin. It can be anywhere you want, but I'm drawing it near the origin. It's a surface, and it's got these outward going normals. And I must take E dot surface area for every face. And I got to get 0. That's a condition. So is that going to work or not? Let us see. There are 6 faces in this cube. So I'm going to draw 1, 2, and 3 that I can see. And -1, -2, and -3 refer to the faces on the opposite side. Okay? This is 3, that's -3. So I can only show you 1, 2, and 3. Let's look at surface 1 and ask what I get from the surface integral of E. Do you agree that E points this way? So E dot dA is a non-zero contribution on surface 1. But on surface -1, E still points up, but dA points down. Because E doesn't vary from the upper face to the lower face, because in going from upper to lower, I'm varying the coordinate z, but nothing depends on z. The same electric field is sitting on the upper plane of this cube as on the lower plane of the cube. Therefore, the surface integrals will cancel and give you 0 because the area vectors are opposite. That is a simple statement that if you got a constant electric field going through a cube, the net flux will be 0 because what's coming in on one side goes out of the other side. So that's the cancellation of 1 and -1 give me 0. But there are other faces like 3 and -3. What surface integral will I get from 3? Look at the area vector looks like this, the electric field looks like that, and the dot product is 0. In other words, the field lines are parallel to this face, so they're not going to penetrate it, you're not going to get any flux, or the area vector is perpendicular to the field vector. So on this face, it is 0, on the opposite face is also 0. The same thing goes for 2 and -2. If you go to face number 2, here the electric field is pointing like that, but there is no flux, and there's no flux on the opposite face. So we get 0, either because the field is parallel to the face, or if it's perpendicular, it has the same value on opposite faces with opposite pointing normals or opposite pointing area vectors, and you get 0. So that's how you get the surface integral of E to be 0 on this tiny cube. But if it's 0 on a tiny cube, it's 0 on anything you can build out of tiny cubes. That means 0 on any surface. If you repeat the calculation for B, you'll get pretty much the same logic, except that B now points like this. So on the top face, B will have no flux because it's running along the face. There is no flow through that. Top and bottom are 0 and 0. The only faces which matter are 2 and -2, because 2 is coming out of the board and B is coming out of the board. But on the other face, which you cannot see, the -2, B is still going this way, but the area vector is going the opposite way. The key to this is that B does not vary. You see, if the flux was not constant, if the field was not constant, the fact that you got two faces with oppositely pointing area vectors doesn't mean the answer is 0. Even though the area vectors are opposite, the field strength could be bigger on one face, smaller on the opposite face, in which case they won't cancel. But the field is not varying in the coordinate in which I've displaced the planes. That's the reason you get 0 for both of those. All right. So far, what I've shown you is that the solution I have automatically satisfies 0 surface integral without any further assumptions. Of course, it's very important that E did not vary with X or Z. But with the assumed form, I don't have to worry. I still have to only worry about the other two Maxwell equations involving line integrals. Got to make sure that works out. So let's see. So here, I have to take loops. And I told you, when you take loops now, you got to take loops in that plane, and that plane. Because it takes three kinds of little Lego flat pieces to form a curved surface in 3D. So let me take this loop first. I want to take an infinitesimal loop that looks like this. And I choose the orientation of this so that if I do the right-hand rule, the area vector is pointing in the positive y direction. In other words, this is a tiny loop of size, what, delta y, let's see, delta x this way and delta z that way. And the area vector is coming out like that. So I have to now look at the line integral of E dot dl and equate it to minus d phi b dt. I have to see, is that true or false? Well, take this loop and look at the line integral of E and see what happens. There is an E going up this face. E is perpendicular to that face, and E is perpendicular to that edge. E is anti-parallel to this edge. You see that? If E is pointing up, it cancels between these two. These two have no contribution because E is perpendicular to dl. But these two cancel. They cancel again because the E that you have here going up is the same E that you have here also going up, but the dl is going in opposite directions. Therefore, E dot dl around this tiny loop is actually 0. You understand why it is 0? Cancellation between opposite edges and two edges that don't give you anything. So what we hope for is that on the right-hand side, there better not be any magnetic flux coming out of this thing, because otherwise right-hand side will give you a non-zero contribution. But luckily, that is the case because the magnetic field looks like this. It's in the plane of this loop. The dot product of the area vector, which is perpendicular to the loop, and the B field is 0, so that's also 0. So this is identically satisfied on that loop. Now, if you take line integral of B dot dl, and that's supposed to be minus plus mu 0 epsilon 0 d phi dt of the electric flux. Again, you should try to do the exercise with me. Magnetic field, I said, is going in the x direction. So it has nothing to do with those two edges because they are perpendicular to it, but it cancels between these two. It cancels because the edges are going in opposite direction, but B doesn't vary from this edge to that edge because it varies only with y. So again, you get 0. And there is no electric flux coming out of this surface because electric field lines also lie in the plane of that loop. They don't cross it. So those equations are also satisfied. But I'm not done because I still have to consider loops in this plane and loops in that plane. Because so far I've gotten no conditions at all. What this means so far is that there is no further restrictions on EZ and BX. There can be anything you like. But I'm going to get restrictions by finally considering loops in this plane and loops in that plane. So let's see how you get condition on one of them. So this is x, y, z. So let's take a loop that looks like this. I've chosen it so that with the right-hand rule, the area vector is perpendicular and coming out the x-axis. I remind you once again, E looks like that, and B looks like this. So let me give the edges a name, 1, 2, 3, 4. And let's take the condition E dot dl is equal to minus d by dt of the magnetic flux. Now, this loop has dimension dy in this direction, dz in that direction. This is an infinitesimal loop. I've drawn it so you can see it, but it's infinitesimal. Okay, so what do I get on the right-hand side? Right-hand side says minus d by dt of the flux, magnetic flux coming out of the board. The magnetic flux is coming out like this, right? It's coming out of the blackboard, so that really is a magnetic flux. That magnetic flux is the number I wrote down, bx, times the loop area, which is dy dz. That gives me minus delta y delta z bx dt. That's the right-hand side. This loop is so tiny, I am approximating b by the value at the center, if you like. You might say, look, I don't think b is a constant on the loop. B is varying. Why do you take the value at the center? Well, if it varies, the variation is proportional to delta x. I'm to delta y or to delta z. Therefore, there will be a term proportional to delta y square or delta z square. But we are going to keep things to first order in delta y and delta z. So it doesn't matter. Now, how about the left-hand side? If you look at the left-hand side, I hope you'll try to do this one. If you go like that on edge 2, you will get E sub z times delta z. I'm sorry, let me write it as delta z times E sub z at the point y plus delta y. And on this edge, I will get minus delta z times E sub z at the point y. In other words, the electric field is everywhere going up. So it goes up here, dl is parallel to it. So that should be that times delta z. These two don't contribute because E and delta L are perpendicular, so forget that. But this one, it goes in the opposite direction, so I subtract it. But I bear in mind that this is y plus delta y, but that's only y. So here I hope you guys will know what to do. You will say that is then roughly equal to dEz over dy times delta y. Therefore, the line integral of the electric field is proportional to the derivative of Ez with respect to y times the area of the loop. And the surface integral of the flux change is also proportional to the area of the loop, and you get dBx dt. So this is the final equation you get by considering that loop. So what is remarkable is the line integral and the surface integral are both proportional to the area. The surface integral being proportional to the area of the loop is obvious because it's a surface integral. Why is the line integral proportional to the area? Because one part of the line integral is the width of the loop, delta z. Other one comes in because the extent to which they don't cancel is due to the derivative of the field in the transverse direction. That brings you a delta y. So if you cancel all of this, you get the equation that I'm interested in, which is very important. dEz over dy is equal to minus dBx dt. This came from looking at this equation. The last one, another loop equation I'm going to go through somewhat quickly because it's going to be 0 equal to 0. Suppose I take the integral of the magnetic field around this loop. Do you understand why it is 0? The magnetic field is coming out of the blackboard. DLs are all lying in the plane. So line integral of B is then 0. And that better be equal to minus mu 0 epsilon 0 d phi electric dt. That is the case because there is no electric flux coming out of this phase. The electric lines are in the plane of the loop. There is no electric flux. There is no rate of change. So it's 0 equal to 0. So from this loop, I managed to get one equation. So my plan now is I don't want to do yet another loop because it's going to be either you got the idea or it's not going to help to draw one more loop. But I will just say that if you draw the last loop, which lies in what plane? Which lies in this plane, you will get one more equation. I'm just going to tell you what it is. So I got d Ez dy is minus dbx dt. And you'll get another equation, dbx dy is equal to minus mu 0 epsilon 0 dEz dt. So I confess that I have not derived this one, but it's going to involve just drawing one more loop and doing it. Now it's really up to you guys how much you want to do this, but you should at least have some idea what we did. It turns out these are the only restrictions I have to satisfy. If this is true of my fields, I'm done because I've satisfied every Maxwell equation. Every surface integral was 0 on every tiny cube and therefore 0 everywhere for E and B. The line integrals, some were identically satisfied, some were 0 equal to 0. There were some that led to non-trivial conditions, and it's these two. Therefore, I'm told that if the fields that I pick that depend on y and t have the property that the y derivative of this guy is the t derivative of that guy, and the y derivative of bx is up to some constant, the minus t derivative of the other guy, you're done. That's all you require of that function. So let's do the following. Take this equation, take its y derivative of both sides. In other words, I want to take y derivative of this, and I want to take y derivative of that. Then here you will get d2 Ez over dy square is equal to minus dbx dy dt, right? Take the d by dz of this. Now you know partial derivatives. You can take the derivatives in any order you like. So let's write it as d by dt, d by dy. But dbx dy is mu 0 dEz dt. Another dt makes it plus mu 0 epsilon 0 d2 Ez over dt squared. Right? Take first the y derivative. Dbx dy is that one single time derivative. Take one more time derivative, you get this. And now we get this wonderful, we really have the wave equation now because I get d2 Ez over dy square minus mu 0 epsilon 0 d2 Ez over dt square equal to 0, which you recognize to be the wave equation. Because that's what the wave equation looks like in the top of the blackboard. But the things that are oscillating now is not some string. It is really the electric field oscillating. It's not a medium that's oscillating. There's nothing there. This is all in vacuum. So let's find the velocity. V squared will be 1 over mu 0 epsilon 0. Right? Because this thing that comes in the wave equation is the 1 over v squared term. Then you go back to your electrostatics and magnetostatics and find out what these numbers are. And I remind you that 1 over 4 pi epsilon 0 is 9 times 10 to the 9, and mu 0 over 4 pi is 10 to the minus 7. So let's write this as 4 pi over mu 0 times 1 over 4 pi epsilon 0, because we know what those guys are. So 1 over 4 pi epsilon 0 is 9 times 10 to the 9, and 4 pi over mu 0 is 10 to the 7, so you get 9 times 10 to the 16. Or the velocity is 3 times 10 to the 8 meters per second. So this was the big moment in physics when you suddenly realize that these things are propagating at the velocity of light. So people knew the velocity of light from other measurements, got a fairly good idea what it was. They knew mu naught by doing experiments with currents. They knew epsilon 0 from Coulomb's law. And it's one of the greatest syntheses that you put them together and out comes an explanation. Now, this doesn't mean that electromagnetic waves is the same as light. You agree that if you run next to a buffalo at the same speed, you are not a buffalo, right? You just happen to have the same speed. So that was a bit of a leap to say it is really light. But it was also known that whenever you have sparks in electrical circuits and so on, you see light. So it took a little more than that, but it's quite amazing because gravity waves also travel at the speed of light. So you cannot assume that the speed means the same phenomenon. But they were right this time. That really was the speed of light. So we now have a new understanding of what light is. Light is simply electromagnetic waves traveling at the speed, and it consists of electric and magnetic fields. And what we have is an example of a simple wave, but one can show in general that if you took the most general E and B you can have, you will get similar wave equations. You will get it for every component of E and every component of B. So waves in 3 dimensions will satisfy the general wave equation. But I'm not interested in the most general case because this is enough to show you where everything comes from. So you have to think about how wonderful this is, because you do experiments with charges, with currents, and you describe the phenomenology as best as you can. Then Maxwell added that extra term from logical consistency by taking this capacitor and drawing different surfaces and realizing that unless you added the second term, d phi e dt didn't work. And without the second term, you don't get the waves. It's only by adding the second term and then fiddling with the equations, he was able to determine that this can have waves can travel. So the reason the electromagnetic waves travel in space without any charges is once you got an E field or B field somewhere, it cannot just disappear. It's like the LC circuit. If your capacitor is charged, by the time it discharges, it has driven a current in the inductor. Inductor is like a mass and it's moving the velocity. Current is like velocity. So it won't stop. So the current keeps going till it charges the capacitor the opposite way. Then they go back and forth. There you have only 1 degree of freedom, which is the charge on the capacitor or the current in the circuit, which are related. Here E and B are variables defined everywhere. But you cannot kill E because the minute you try to destroy E, you will produce a B. The minute you try to destroy B, you will produce an E. So they keep on swapping energy and going back and forth. So it is self-sustaining, and it's an oscillation, if you like, but it's an oscillation over all of space and not over 1 or 2 degrees of freedom. So I'm going to now write down a specific form. Now, the specific form I'm going to write down looks like E equal to what? K times E0. Now I'm going to pick a particular function, ky minus omega t, and I'm going to pick B to be I times B0 sine ky minus omega t. Now I'm making a very special function of y and t. Till now, I just said it's a function of y and t. All I needed was it's a function of y and t. That was enough to get me all this. I'm going to find a relation between these constants, E0 and B0, by putting them into this 2 Maxwell equations I had. That's all I want to do now. So one condition I had was dEz over dy was minus dBx over dt. Then I had dBx over dy is minus mu 0 epsilon 0 dEz over dt. These are the two equations. I'm going to demand that these particular functions obey these two equations. If they obey these two equations, they will obey the wave equation, because when I combine this equation with that, I got the wave equation. You understand? When I have an equation A and an equation B, if I put one into the other, I got the wave equation. But you really should satisfy separately equation A and equation B, because it's not enough to satisfy the one you get by shoving one in the other. You should be true independently. So let's demand that this be true and demand that be true. So what is dEz dy? If you take the d by dy of this is what I call Ez, and this is what I call Bx. dEz dy, if you take the d by dy of that, will give me k E0 cosine ky minus omega t, and we want that to be equal to minus dBx dt. So take the d by dt of this guy. D by dt of this guy is B0 minus omega cosine ky minus omega t. So these things cancel out, then I get B0 omega. So this tells you that E0 is equal to omega over k B0. It tells you about the magnitude of the E and B vectors, what size they should bear in relation to each other. This is one condition. I'm almost done. So I want to take this condition now. So dBx dy, what is that equal to? B0 k cosine ky minus omega t is equal to minus mu 0 epsilon 0 dEz dt, which will be minus omega E0 cosine ky minus omega t. Cosines cancel. Then I get a condition B0k is equal to mu 0 epsilon 0 omega times E0. But that is equal to omega over c square times E0. Because mu naught epsilon naught is 1 over c squared. So I get a second condition, which I can read as E0 is equal to c squared over omega times B0. So these are the two conditions in the end. If you want the function to look like this traveling wave with sine waves in it, then the amplitude for E and the amplitude for B have to satisfy these two conditions. But look at these two equations. They're both telling you something about E naught. One says E naught should be omega over k times B naught. Other says E naught should be c squared over omega times B naught. That means omega over k better be equal to c squared. I bet I dropped the k somewhere. B naught k, thank you. Yes, so c squared k over omega. That tells me that omega square is equal to k square, c square, or omega equal to kc, or plus or minus. Or if you like, k is plus or minus omega over c. Doesn't matter how you write it. But you can see what that means. What this is telling you is that if you take the function sine ky minus omega t, and if omega is equal to kc, it becomes sine of ky minus kc t. That becomes sine of k times y minus ct, which is a function of y minus ct. In other words, we knew this was going to happen because the wave equation says the function should be a function only of y minus ct. That will happen if omega equal to kc. You see that if omega equal to kc, you pull the k out, you get y minus ct. Or you can have y plus ct, but my solution was y minus ct. I'm almost done. So the last thing I want to get from this same equation, now that that condition is satisfied, if omega is equal to kc, I get E0 equal to c times B0. So now I'm going to summarize this. Don't worry about the details. Now I will tell you the part you should know all the time. So I know this is somewhat heavy. I mean, I had to do this calculation at home to make sure I got all the minus signs right. There's an RG of minus signs. I'm not that interested in that. I know that you guys, unless you're going to major in physics and want to do it for a lifetime, don't want to know all that. So what should you know? What you should know is that by doing a few experiments, one wrote down these Maxwell equations. You got to understand a little bit where everything came from. Then the whole class was demonstrating that they implied some waves. And the demonstration was shown by proving it for infinitesimal loops and infinitesimal cubes, and then seeing what conditions I had. And I found that I can get a set of functions that are dependent on y and t, and that they really travel at the speed of light. So that was the bottom line. Actual derivatives and how everything happened is really not something I expect you to carry in your head. Okay, so don't let the exams ruin that for you. I don't care. I will not quiz you on that part of this derivation. But you must understand that the structure of physics was such that it was an interplay between some experiments and some purely theoretical reasoning on the nature of equations. And you put them together, and what makes it worthwhile in the end is to get fantastic predictions like this that unify electricity and magnetism and light into one shot. So the picture I get now, if you look at all of this, the final answer is E looks like K times some number E0 sine ky minus omega t, but I want you to know that omega is equal to kc there. Then I get B equal to I B0, also the same sign, with the extra restriction that B0 times C is E0. So here's what the electromagnetic wave looks like. One guy, the electric field, is always living in this plane. This is the E field. At one instant, if you take a snapshot, that's what it'll be doing. Going up there, coming down here, going up there. That's E. B field looks like this. Lies horizontal here, goes like that, and comes out. So this is in that plane, and that is in the vertical plane. That's the horizontal plane, that's the vertical plane. So that is E, and this is B. And the point is E over B is equal to C. In other words, E is much bigger than B. And the ratio of them is the velocity of light. This is interesting because if you took the force on a charge, you remember it's Q times E plus B cross B. That means if you took an electron and you left it in an electromagnetic field, the field comes and hits you. The E field is oscillating one way, the B field is oscillating perpendicularly, the wave is traveling in a direction perpendicular to both. If you want, it's in the direction of E cross B, is the direction of propagation of the wave. If it hits an electron there, the oscillating up and down electric field will make the electron move up and down. It will also be feeling a magnetic force, B cross B. But notice that the size of B is the size of E divided by C. So the electric force to magnetic force ratio, or magnetic to electric, will be in the ratio of V over C. So for most velocities, for electrons in circuits and so on, the velocity is much tinier than the velocity of light. So when a radio wave hits your antenna, gets the electric charges in action, it's the electric field that does most of the forcing, not the magnetic field. But in astrophysics and cosmic ray physics, where particles can travel at velocities comparable to that of light, then these forces can become comparable.